Okay, so today I'm going to talk about this topic. I apologize because I think so. I talked some of it in this meeting we had in last December, I think, and I think some people from the audience were there in that meeting, and so it will be kind of a repeat for them. Hopefully, they have forgotten what I spoke at that point. Okay. So you know quantum gases nowadays, of course, is like a hot topic because of these cold atom experiments. You can uh, realize these interacting bosons in cold atom systems. Uh, However, the analytically tractable models of correlated Bose gases are very rare. These are the two notable systems. One is this Lieb-Linear model, and one is this another is this Gross-Petersky equations, which describe this weakly correlated Bose gas, and this is this one-dimensional model. So in this case, the solutions can be obtained in the terms of this Bethe answers, but if you put the system in a harmonic trap, this one cannot solve this problem, so it becomes very hard. Okay, so in some sense, exactly solvable models of interacting Bose gases in a potential is a hard problem. Okay, so this brings me to this motivation of this work. So basically, there is a paucity of analytical tractable models of strongly correlated quantum gases. And even if the solution can be found in some cases like this Lieb-Linear model or this thing, even if you have this solution, starting with the solution, finding some observables which you might be interested in, like for example, extreme statistics or full counting statistics. I'm going to explain what these terms mean. So it becomes very difficult. Okay. So therefore, there is a need for analytically tractable models of correlated quantum gases, which you can also observe experimentally. Okay. So this is what we do, and since the time is short, so this is the most in some sense interesting important slide. So this is our engineered system basically. Okay. So these are the steps. So you have a harmonic oscillator centered around some position A. So you have a harmonic potential, and you have n non-interacting bosons in that harmonic potentials. Okay. And then what you do, so you instantly shift the position of the harmonic potential to from plus A to minus A. So in other sense, you quench this Hamiltonian to this Hamiltonian instantly. Okay, and then you evolve the system unitarily up to some time tau. This you draw from an exponential distribution. Okay, so this R is the rate of this time. Okay, and then after this time tau, you immediately change this state psi t to psi 0. So how do you do that? You reset this. So you can think of it like you again switch your position of the harmonic potential to plus A, and you quench the system to the ground state. So you basically cool the system to the ground state, and there are various ways to cooling the system to ground state experimentally, and we assume that the time which takes to cool the system ground state is very small. Okay, so we don't, in this calculation, we don't take into account the time it takes to cool the system. Okay, and this is this protocol, and then you keep following this step. Okay, so you start with here, quench to this one, let it evolve unitarily from some time tau t, and then you psi t you quench to psi 0, and again you evolve with this Hamiltonian for some another time tau 1, and you keep on doing like this. Okay, so eventually, if you follow this, and this system evolves to a non-equilibrium stationary state, and we want to know what is this stationary state. Okay, this is what we are saying. So this is this unitary evolution. So during this unitary evolution, your psi t evolved by this. So Ht is the Hamiltonian I have shown before, and the density matrix is just given by this. Okay, and given this density matrix, now under this instantaneous intermittent resetting, so you can write down the density matrix for the system, which is given by this one. And given this density matrix, of course, the distribution, position distribution is just the diagonal element of the density matrix. Okay. So this probability density now, in the time t going to infinity, it reaches the stationary state, and this stationary state is very interesting structure. It's a very simple structure. So it has some product structure. Okay, it's just a very simple Gaussian product structure where sigma is just this one, square root of h cross by m omega, and this function h of u is given by this. Okay, So this structure is seen in many other examples, and these are called the CIID structure, in the sense that IID means independent and identically distributed. This product measure is called the IID structure, but it's a conditional IID structure because the distribution is not a product measure, it's conditioned to U, and then you average over this U. Okay, so the distribution of P is not a product structure, but this product structure comes under the integral. Okay, so nevertheless, this, if you have this kind of structure, this makes this problem very simple, analytically tractable. Okay, given this, you can compute various quantities. For example, you can ask what is the average density profile, what is the correlation between particles, extreme statistics, what is the statistics of the rightmost particle, second rightmost particle, and so on. Gap between these particles, okay, if you just order this particle, what is the gap? Full counting statistics, so if you take an interval and ask how many particles are there within that interval, what is the statistics of this, okay? And you can compute all of this explicitly. For example, this is the correlation between any two particles. This is the average density profile, and it has a very interesting structure. This is keeping sigma fixed and varying this resetting rate. This is keeping the resetting rate fixed and varying this sigma. And you see that it has a transition from a single hump to a double hump transition, basically, in both cases. Okay, you can also compute the order statistics. Okay, so order means basically, okay, you look at the rightmost particle, second rightmost particle, and so on. So these M's are these ordered positions, and you can ask what is the distribution of the kth particle. Okay, and it has this. It's in fact directly related to this function h, which we saw in the last case. And this Lk has this nice form. Okay, so you can in fact find when Lk is in the k is in the bulk or k is in the edge. Okay, this is this distribution. Gap statistics again. Okay, it has an exponential distribution with some typical lambda, which is you can find it explicitly. Full counting statistics. There is a number of particle distribution of the number of particle in a given region minus L to plus L. It has this scaling function where this NL by N, it's this parameter K, which is you can think of as a continuous parameter. And naively you will think that, okay, K can be 0, I mean, in principle, K can be either between 0 and 1 because you have all the particles within this or none of this. But what we find is that in this limit, K minimum is strictly greater than 0 and K maximum is strictly less than 1. You can find the expression explicitly. And but yes, just I'm done. So this is basically okay. This is you can actually find a full expression explicitly, but okay, it's interesting to just look at the limiting cases. So what you see is that actually okay, it diverges at both sides as a square root singularity. But what is interesting is that it has a basically jump here. If you just come from the left, it has a finite value, but if you go from the right, it has a diverging distance. So let me just stop it here, saying that basically we have found a exactly solvable model of correlated Bose gas, where the joint distribution has this product form, and given not product form, this CIID form, and given this structure, many of these quantities one might be interested in, you can compute it exactly. Yeah, thank you.
Thank you, sir. Any questions?
It is a Starman, yeah. So what do you do is okay. So you start with first here, okay. So you quench it there, so you immediately change the this thing, so that's okay, okay. Then you evolve unitarily, okay. So now what you do is, let's say you again instantaneously after time t, you bring it from minus A to plus A, connect to a thermal reservoir and you cool it down, so that's a non-unitary process, okay. So that thing, what all the thing I have put it under the carpet because I think that okay, I have not discussed how the system is cooled to this ground state again, but nowadays okay, in the cold atom experiments you can actually do that. Basically, you can just take the system and you can cool it very fast. Basically, so it's basically coupling to a bath, basically coupling to a low temperature bath, and the time it takes to cool down is for our calculation we did not take into account. Okay, so we said that okay, just instantaneous cooling, but okay, you can put some time it takes to cool the thing, and you can still do the calculation.
So can you explain what is the difference from these Bose particles versus non-Bose Fermi particles or such?
The Fermi particle is very difficult actually because, yeah. So, I mean, you can still, so we are still trying it, this calculation. Basically, the problem is that the non-interacting Bose gas, so forget about all these things, right? The ground state, this psi 0, is a product of the individual wave functions basically. But then for the Fermi one, you have to basically construct the Slater determinant, and then you have to do that. And then you have to evolve the whole thing. So this becomes a little bit more complicated, but we are actually working on it. You can, Hamiltonian is a Hamiltonian, you can still do that. I mean, there's nothing wrong with the Hamiltonian. I mean, it's a non-interacting Fermi gas. But even non-interacting Fermi gas, the ground state function is not a product form, right?
Just curious, Sanjib, unequal time correlators is this?
Sorry, say?
Unequal time correlators, for example, in NESS is
we have not calculated. Yeah, we can talk about it, but we have not calculated. Yeah.
If you introduce quadratic couplings between the positions like xj minus xk squared, spring constants or something like that, do you retain analytical tractability? Or?
I think if you have quadratic coupling, you can still do. The reason you can do it because is that, okay, so see if you, the wave function is quadratic, and your, what do you call it, the propagator is also quadratic, right, in this case basically. So if you, even if you have a quadratic coupling, probably you can still do it, but I'm not sure. Yeah, if you can write down the ground state wave function for the n bosons with quadratic coupling.
You have to do more decomposition or something like that.
Yeah, yeah, you can probably.
The reason why I'm asking that is, in that case, the spatial locality will matter. Like
it will. Yeah. Yes. Yeah. Yeah. As long as you keep it within quadratic, we are fine. You have to do, I guess, longer calculations, but it's okay.
Let's thank our speaker.